So the problem is, let f of z be e to the minus z to the minus 4 when z's not equal to 0, 0 when z's equal to 0. We have to show that Cauchy-Riemann equations hold everywhere in the complex plane, and then we have to ask the question, is f entire? That is f differentiable at every point in the complex plane? So the first part of the answer is that if z is not equal to 0, then f of z is just e to the minus z minus 4, and this is a function, a composition of differentiable functions, and that means that f itself is differentiable. And that means so that the Cauchy-Riemann equations hold. So the question is really what happens at 0. And the trouble is that at 0, f has got a different definition to when f is not equal to 0. Now, how do we proceed? So, let's imagine that we write, as usual, f of z is equal to u xy plus I times v xy. That's when z is equal to x plus iy. And let's try and compute. Let's see if we can compute du by dx at 0, 0. Because we're trying to find out what happens when z is equal to 0. That's to say when x and y are both equal to 0. Well, this is equal to the limit as h goes to 0, and here h is a real number, of u of h0 minus u of 0, 0 over h, which is equal to, well, u is the real part of f, so that's the real part of, and h0 corresponds to h plus i0, which is just h, real part of e to the minus h to the minus 4, minus u of 0, 0, well that's the real part of f of 0, which is just 0, over h, and I guess we need to have here a limit as h goes to 0, and h is always a real number. So, h is a real number. This means we've got an exponential of a real number, and so this is automatically real. So we're looking at the limit as h goes to 0, and h is real, of e to the minus h minus 4 over h. Now, this is a nasty limit. The way that we deal with it is we put k equals 1 over h, and we're looking at the limit as k goes to infinity, k is always real, of, well, when we put in h equals 1 over k, we get a 1 over k in the denominator, which is the same as a k in the numerator, and when we put in k equals 1 over h, this e to the minus something is the same as having e to the plus something in the denominator, and that something is e to the k to the 4. Now, if we apply L'Hopital's rule to this and differentiate, on the top line we get 1, on the bottom line we get 4k cubed times e to the k to the 4th, and we can see easily that this is equal to 0 by L'Hopital. Okay, so that says that du dx is equal to 0. Now we need to look at dv dy, and again we're doing this at 0, 0. Now, this is equal to limit h goes to 0 of v of 0h minus v of 0, 0 over h, and this is equal to limit h goes to 0, and I should say again h is always real, just to make sure that we remember that. Now, v is the imaginary part of something. Now, 0h is x equals 0, y is equal to h, so this is the imaginary part of e to the minus ih minus 4 minus, much as before, 0 over h, and that's equal to, well, what is this equal to? Let me forget for the moment about the limit stuff. We're looking at the imaginary part of e to the minus. Now, when I take I to the minus 4, I get just 1. So h minus 4 minus 0 I can forget about over h. Again, I should have a limit here. But notice that h is a real number. I'm looking at h real. H to the minus 4 is real. This is an exponential of something real. It's real. Its imaginary part is 0. So this is just equal to 0. So at this point, we've established that du dx is equal to dv dy. And in much the same way, we can also establish the other of the equations, namely du dy is equal to minus dv dx. They're both equal to 0. So the Cauchy-Riemann equations hold. Now, the question is f entire? And the answer to that is no. F is not an entire function. The reason is that f at 0 is not even differentiable. In fact, if we look at 0, we can even establish that f at 0 is not continuous. We've seen that as we approach 0 along here or here, then we're dealing always with something that involves an exponential with a minus h to the minus 4, and this was always going to go to 0. But if we approach 0 along something like this, then the effect is that instead of having an h to the minus 4 or an ih to the minus 4, we have something whose fourth power is not equal to 1, and at that point we see, in fact, that if we approach 0 along here, here we're saying that the argument of h is, say, pi over 4, then the limit as e to the minus z minus 4 is actually equal to infinity. So at this point, we can certainly say that f is not even continuous at this point, so it's certainly not differentiable. Certainly not entire. That's it.